Welcome everyone to the fifth of the 5 Jigsaw talks. Project Jigsaw, Under the Hood. Quick poll. Who has been to all 5? Some, oh, okay, a small number of hands. Okay, so people have 4. Okay, yes. So people have, this is a serious question, people have been picking and choosing when we've had a sequence of Jigsaw talks. People have been picking and choosing which ones to go to? Yes? Okay. Interesting. Oh, we have another 5-star. We have 2 5-star attendees at the front. I think you've probably been to all 5. One of them twice. Oh, but now you're in the 5th one. Let's go with that. Oh, okay. So, anyway. My name is Alex Buckley. I work in the Java platform group at Oracle, and this is the deep dive, behind the scenes, under the hood, what's really going on with class loaders in JDK 9 that tries to explain some of the statements you may have heard in other talks, talking about the JEPs that are in JDK 9. Sometimes some statements are made that seem to be a bit confusing, and I hope this talk will explain what's really going on. So in JDK 9, but it's standalone, so I still need to introduce that in JDK 9 the main feature is a module system that lets code be more reliable and maintainable. We've used the module system to turn the monolithic JDK into the modular JDK, that is breaking up the rt.jar file inside the JDK into dozens of reusable modules. JDK 9 also has small enhancements to the Java language and somewhat larger enhancements to the standard libraries. Plus, Javadoc gets a search box, and the JDK via JShell includes a REPL at last. Round of applause. I can hear it in my head. So Project Jigsaw is a project led by Oracle in OpenJDK. It's the container for all of our work, building a module system and modularizing the JDK. We're standardizing the module system in the Java community process through JSR 376, and we're standardizing the structure of the modular JDK in the Java community process through the umbrella JSR for Java SE9. So when you use JDK 9, you're always subject to the rules of the module system. That's what's under the hood. And it's what most of this talk is about. Though I'll touch on some aspects, some of the impact of the modular JDK near the end. This talk has 4 parts. The first part explains how the module system works with the Java language and VM to improve the reliability of your code. The second part is really about migrating to modules. The third part explains what the module system is fundamentally capable of beyond what you can express in the Java language. And the fourth part is about the road to JDK 9 and some of the things you should watch out for while traveling on it. So, first part. Everyone knows the hierarchy of accessibility in the Java language and VM. It's simple to understand, easy to use, and strongly enforced by the compiler and VM. But it has a big weakness. The only way to share code between packages is with public. But then you're sharing with everyone. It's not surprising that package friendship in one form or another has been requested many times over the years. One goal of the module system is strong encapsulation, to allow a component to declare which of its public types are accessible to other components and which are not. The lines in italic are the levels of accessibility in JDK 9 connected with the module system. Reading upwards, you can arrange for public types to be accessible only within their module, or accessible within their module and to other specific friend modules, or accessible to everyone, as was in JDK 8. So, as usual, migration drives a lot of our thinking. We want to make it easy to place an existing package into a module and immediately give that package the benefit of strong encapsulation. We don't want each and every public type in a package to have to opt in to strong encapsulation. So public types in a package are not accessible outside the module by default. That is, public on a type declaration no longer means everyone can access the type. What happens if someone tries to access a public type that's not accessible? Here's a slightly aging but very interesting example from Glassfish 4.1. At the time of screen grabbing, it didn't start on JDK 9 because the VM threw an illegal access error. I don't expect you'll be able to read the ring text, but it says, illegal access error, class ComSun Enterprise Security Provider Policy Wrapper in Unnamed Module, don't worry about that yet, cannot access class Sun Security Provider Policy file in module Java base. The point is that the class Sun Security Provider Policy file is declared public. But since it's a JDK internal API, it's now accessible only within the Java base module. Sorry, Glassfish, you need to find an alternative security API. In JDK 9, modules are first-class program components like classes and interfaces. Here's the declaration of the Java SQL module that contains JDBC. It's in a file called modulinfo.java in a directory named after the module, java.sql. The compiler treats this like any other Java file and translates it to modulinfo.class, which you can put in a jar file as normal. We would call that a modular jar. The package hierarchy exists in the same directory, source Java SQL, as modulinfo.java. So modulinfo.java is outside of all of the packages in the module. That's because it's the job of the module declaration to say whether a package is strongly encapsulated or not. It's easy to get strong encapsulation for the types in your packages. Don't mention the package in the module declaration. To allow other modules to access one of your packages, or more specifically the public types of your package, just add an exports clause. As I said, you can export to all other modules, as is happening here, or you can say exports to give access to only your friend modules. At compile time, Java-C prevents code outside the Java SQL module from accessing the public types of any packages in it except for those 3 packages listed. You get the same compile time error as when you try to access a package private type from outside its package in JDK 8. And then at runtime, if you somehow built the class files by hand, at runtime the VM throws an illegal access error like you saw with Glassfish if you try to access the public types of anything except those 3 packages. Let's dive into the VM more deeply. Traditionally, accessibility in the Java platform is about who is doing the access and what is the public protected private flag on the target class. At runtime, the VM uses the class loader of the accessing class to find and load the target class, and then the VM checks the flag, public protected private, of that target class. Now, because the VM relies on class loaders, people can create loaders that only know how to find and load classes of certain packages. In effect, loaders can isolate one package from another. In the top picture, class p.c is trying to access class q.d. The loader for p.c knows to delegate, it just bear with me, it knows to delegate to another loader for any class in package Q, such as q.d. Only when that other loader has found and loaded q.d can the VM check its flags to determine if it's public enough for p.c to access it. Now in the bottom picture, the loader for p.c has no idea where to find package Q, so no access to q.d is possible from p.c. Technically, this isn't a failure of accessibility, since the VM never actually gets to load, never gets to check the flags of q.d. Instead, it's a failure of visibility. Q.D is invisible to P.C because the class loading couldn't find Q.D. Still, the effect is quite powerful. If the class loader of the accessing class, P.C, cannot find and load the target class, then it doesn't matter if the target class is public. It's effectively encapsulated. So whoever sets up the class loaders sets up this effective encapsulation. The thing is, though, that encapsulation based on class loaders is not strong encapsulation, sad face. It relies on packages being carefully apportioned into different loaders, but that isn't how the JDK has ever worked. Most code in the JDK is loaded by the Bootstrap or platform class loaders, while code on the class path, all of it, is loaded by the application class loader. Spinning up lots of loaders for all of this code to try and isolate it and to try and encapsulate it would be a compatibility nightmare. And in any case, there is no actual isolation. You can circumvent class loaders by getting hold of references to Java-lang class objects, which you can always do for any object. And then once you have a class object, the class loaders are irrelevant. And it's impossible to stop references to class objects from being passed around. Strong encapsulation is about being able to prevent access, even if the accessing class and the target class are in the same class loader, such as the application class loader. And even if someone is using core reflection to manipulate class objects. So let's assume that multiple modules are somehow mapped to the same class loader. Can class P.C in module X access Q.D in module Y? Another goal of the module system is reliable dependencies to replace the brittle, error-prone class path mechanism with a means for program components to declare explicit dependencies on one another. So in order for P.C to access Q.D, not only does module Y need to export package Q, but module X needs to somehow explicitly depend on module Y. The formal name for depends on is readability. Readability underpins accessibility in the Java language and VM in 9. The accessing class, P.C, must be in a module that reads the module of the target class, that is, reads module Y, and the module containing the target class must export its package to at least the module of the accessing class. So accessibility is a two-way street. Module X reads module Y, and module Y exports this interesting package Q to at least X. Note with these arrows that accessibility is independent of class loaders. I don't need to talk about the class loaders on this slide, just like accessibility was before the module system. This is important for two reasons. It means accessibility works at compile time when there aren't any class loaders. Second, it means you can reason about accessibility based solely on the requires and exports clauses in module info.java files. There's no need to worry about which class loaders will come into existence at runtime. In fact, the exports part of accessibility is fairly straightforward. A package is either exported or it isn't. But on readability, there's more to say. When you depend on a module, you depend on a hopefully coherent set of packages that it exports. That's its surface. In some sense, those packages are the interface of the module. Inside the module, hundreds more packages may sit, strongly encapsulated, not exported, not for you, waiting to help implement that interface. And more than that, when you depend on a module, you indirectly depend on all of the modules it depends on. For example, if you depend on the java.activation module in the JDK with its 35 classes, then you indirectly depend on the java.desktop module in the JDK with its 5,835 classes. If the watchword for JDK 8 was functional, then for JDK 9, the watchword is transitive. You should think in terms of the set of modules needed transitively by your application. That is, the indirect dependencies can be as important as the direct dependencies. Let's see how readability models this. I'll use an example of readability from the graph of JDK modules. The Java SQL module that holds JDBC requires the Java logging module that exports the package Java util logging. This requires clause means that code in the Java SQL module can access the public types of Java util logging, such as logger. You can see that some code in the JDBC driver manager class on the left is newing an instance of logger. Fine. What if it was the API of the Java SQL module, rather than its implementation, that wants to use the logger type? In other words, logger is in a method signature, a public method signature of a public interface in an exported package. So what if that API wants to refer to the logger type rather than some method body? So here the JDBC driver interface wants to return a logger. Let's look at this through the eyes of an application module that uses JDBC, MyApp. In order to use to call that driver method that returns a logger, the MyApp module not only needs to read the Java SQL module, but also the Java logging module, which exports logger. It would be a pain if the developer of MyApp had to remember to say requires Java logging when using a particular part of the API of Java SQL. Sad face. There's good news. The Java SQL module can take on the responsibility of remembering. Look at the Java SQL module. It now says requires transitive java.logging. The word transitive here means that anyone who reads the Java SQL module also reads the Java logging module for free. The MyApp module no longer has to bother with requires Java logging because it reads Java logging thanks to reading Java SQL. Happy face. This is called implied readability, and it's very powerful. It's powerful because it lets a module be refactored without breaking consumers. For example, suppose that Java logging has some auxiliary packages that we'd like to start shipping in a separate module, log extras, ... stuff in it, some exports. The Java logging module can say requires transitive log extras, so that MyApp, which already implicitly reads Java logging, also implicitly reads log extras. MyApp would be unaware that this refactoring down the stack is happening. It just says requires Java SQL. So in essence, this model of readability supports downward decomposition. Any module you read can be decomposed by its author into new modules, and readability of the new modules can be recovered with a requires transitive clause in the old module. So you can see that the definition of reads, one module reading another, is recursive. A module X reads another module Y by requiring it directly with a requires clause, or by reading some third module Q, there's the recursion, reading some third module Q, where Q says requires transitive Y. And now that X reads Y, Y can say requires transitive for some other module, and X will read that too. Now be careful. Once people require your module explicitly, you can refactor it downwards as much as you like, but you cannot delete it. There's no way for a module to stand in for another module by taking its name as an alias. If someone requires X and X is deleted, then the module system won't start. I said earlier that the exports part of accessibility is pretty straightforward. A package is either exported or it isn't. But it's actually a little more subtle than that. Here are some of the exports of the Java base module. Exporting a package means that anyone can compile and run against its public types and their public elements. There are dozens more packages in Java base that aren't exported. No one can compile against their public types. Even if you make a class file by hand that refers to a public type in a non-exported package, it won't run. This isn't just compile time trickery. The VM's doing it as well. But still, that's all accessibility in the Java language and VM, where the accessing class and the target class are known statically. It's in the source code or the bytecode. What about accessibility with reflection, where the target class is only known dynamically? We think it's very important that exporting a package like Java security, yep, there it is, for static access to be programmed against, does not mean that anyone can reflect over the internals of that package. Because if they can, they will. Here is a Stack Overflow question from July 2016. Someone, this is really, you can take a picture of the URL. Someone was using setAccessible to access a private field in the class Java Security Key Store. The purpose of the class Java Security Key Store is, and I quote, a storage facility for cryptographic keys and certificates. If ever there was a class whose private fields should be inaccessible, it is this one. Now, the Java security package is exported so you can code against the public type key store and its public fields and methods, not so that you can reflect over key store's internals. Ringed code. I love the first answer. How, after updating, something's not working, how can I fix it? You solve it by not fiddling with private data members of other classes. First answer. So, just exporting a package, exports P, does not allow reflection to access the non-public elements of the package, the non-public types, or even the non-public elements in public types. So, I'll say it again. If you obtain a class object for a non-public type in the package, you can still list its members, but you cannot call get or set on its Java-lang reflect field objects, even for a public field, because it was a non-public type. Nor can you call invoke on its Java-lang reflect method objects, even if a method is public, because it was a non-public type. Similarly, if you somehow obtain, maybe someone passes it to you, a Java-lang reflect field object for a private field in a public type, you cannot call get or set on it. And even calling setAccessible won't help. If the author of the module really wants to allow access to non-public elements via reflection, this can be expressed with exports privates. And that then allows reflection to work as it did in JDK 8. Private members of public types can be accessed, and public members of non-public types. We don't officially call it weak encapsulation, but you can think of it that way. The bottom line is that strong encapsulation is even stronger than the powerful reflection capabilities traditionally offered by the Java platform. It's up to the module author to choose strong encapsulation, and if they do, via a plain exports, as we do in Java base, there is no way for another module to break in. The module system API does not allow one module to augment the exports of another module reflectively. A module can only augment its own exports via the API. So setAccessible's behavior now depends on the module author's choice of how a package is exported. And of course, for Java security, public types, no problem. Public methods in those public types, no problem, code against them. But private things inside, you can't touch them. There is a question. There are lots of questions, but I will take them at the end. Thank you. Accessibility used to be a simple check, basically for public or same package at compile time and runtime. In JDK 9, accessibility is the mechanism for strongly encapsulating module internals. Accessibility relies on readability, which can be direct or implied. And accessibility is enforced by the compiler, VM, and reflection in line with the module declarations. Part 2. Everything so far has been about named modules, modules explicitly declared with a name in module.info.java. What about jar files on the class path that don't have a module.info.class file? They seem to be in a world of their own. To keep the model of accessibility and readability consistent, we introduce the unnamed module. All classes not in named modules are in the unnamed module. It's as if, wait for it, everything on the class path is in one big module. And because it's a module, we can ask two questions. What does it read and what does it export? What it reads is simple. Every named module, all of them, as if by magic, for free. This means anything exported by a named module can be accessed by code in the unnamed module. You can turn a jar file into a named module by adding module.info.class and putting the jar on the module path where named modules are found. Jars left on the class path will not realize that anything happened. They can still read those named modules. That's a huge help for migration. The next question is what the unnamed module exports. Before that, though, we should ask, who reads the unnamed module? Remember, our goal in the module system is reliable dependencies. We believe very strongly that named modules should not read the unnamed module out of the box. It would make a mockery of reliable dependencies to let named modules depend on the arbitrary content of the class path. So you cannot write requires unnamed or requires class path in module.info.java. There are no reads edges going out to the unnamed module. This seems like a huge hindrance for migration because any jar you turn into a named module can't access the jars left on the class path. The answer is automatic modules. You can take a jar, say guava.jar, and move it from the class path to the module path. That turns the jar into an automatic module. That's all you have to do. An automatic module is a named module, declared implicitly rather than explicitly. Its name is derived from its jar file name in obvious ways. Placing guava.jar on the module path gives an automatic module called guava. As before, whenever you see a module, you should ask, what does it read and what does it export? The automatic module guava reads everything in the JDK and the unnamed module. It's as if it says requires unnamed. Now the hindrance to migration is gone. You can turn a jar into an automatic module, and it can still access the jars left on the class path. We asked earlier what the unnamed module exports. The answer is all its packages in junit.jar and glassfish.jar and hibernate.jar, precisely to help code in automatic modules which read the unnamed module. And it's a full power export as well. You can reflect back in. Because an automatic module is a real named module, another named module can require it. Suppose the myapp module says requires guava. So there's a reads edge then from myapp to guava. What does an automatic module like guava export? That's easy. All of its packages, including for reflection. So myapp can access all of the public guava types and reflect over it, no problem. Myapp could even say requires transitive guava to transmit its dependency on guava up to its own consumers, so that anyone who reads myapp would read guava for free, even though guava is an automatic module. So by moving a jar from the class path to the module path, you get an automatic module that lets you start building up your own graph of modules. It's not necessary to wait for every jar on the class path to be modularized by its author before you start developing your own modules that require it. So there are three kinds of modules: explicit named modules, like JavaSQL, automatic named modules, like Guava, and the unnamed module, aka the class path. And the key point is there is lots of readability for free to help with migration. And since the readability underpins the accessibility, you then get a lot of accessibility as you had on JDK 8. Loaders and layers. I said before that strong encapsulation is independent of class loaders. This means that the model of class loading in JDK 9, is unchanged. The mechanism of loader constraints, for those of you who have been reading the VM spec, is unchanged. The notion of runtime packages is unchanged. The Java-Lang class loader API is essentially unchanged. Class loading doesn't change in JDK 9. In addition, the actual class loaders, the actual objects in JDK 9 are the same as in JDK 8. There is the bootstrap loader, there is the platform loader, used to be called the extension loader, too confusing, call it the platform loader. And then there is the application loader, which loads everything on the class path, all on top of the VM. Traditionally, the vast majority of JDK classes were defined by the bootstrap loader. Critical JDK modules, such as Java-Base, still have their classes defined by the bootstrap loader. For non-critical JDK modules, it is important for security to move their classes out of the bootstrap loader if possible. Modules in the bootstrap loader run with all permissions, which is not ideal from a security perspective. Those modules can only be deprivileged, that is, run with fewer permissions, if they're not in the bootstrap loader. So in JDK 9, all the modules containing Java EE technologies, such as java.corba, have been moved, as well as the JDBC modules, JavaSQL and JavaSQL Rosette. Their classes are now defined by the platform loader. Frankly, moving a module as big as Java Corba, 1,831 classes and 31 exported packages, is no small accomplishment. The deprivileging work itself of specifying the fewer permissions will continue for many years. The application loader is then responsible for everything else. A number of JDK tool modules, such as JDK compiler, have their classes defined by the app loader. All classes in modules on the module path, whether they're in a modular jar or in an automatic module like Guava, are defined by the application loader. And all classes on the class path in traditional jar files like junit.jar and glassfish.jar are defined, as before, by the application loader. A couple of notes on compatibility. First, frameworks that delegate directly to the bootstrap loader to find JDK classes might break on JDK 9 because many JDK classes aren't there anymore. Frameworks should use the new class loader method, getPlatformClassLoader, which returns a loader guaranteed to provide visibility of exported JDK classes. Second, the application loader, whilst there still is one, the object itself is no longer an instance of URL class loader. Frameworks that assume it is, in order to hack via setAccessible into its addURL method, sad face, will break on JDK 9. The only supported way to dynamically extend the class path is with the class path attribute in jar files or with the agent API in Java-Lang instrument. Now, you may be wondering where the module system itself lives in all of this. It's important to realize where the module system isn't. Traditionally, A module system was simply Java code that acted as a factory for class loaders. It created loaders that defined classes found in some modular artifacts, and then those loaders delegated to each other in accordance with some kind of modular imports and exports. As I mentioned before, there is then some encapsulation for classes because those loaders, A, B, and C, can hide classes. They can isolate classes from each other. A module system that does this will still work on JDK 9 because class loading hasn't changed. But the module system in JDK 9 is quite different. The module system in JDK 9 is not a factory for class loaders, but rather a conduit, a transmission mechanism that allows modules to be communicated to the VM. Whoever creates the class loaders is responsible for using the module system API to transmit module names, contents, dependencies, and exports to the VM. That's how the VM knows enough to enforce accessibility. It's also how the core reflection API can enforce accessibility, since core reflection is based on VM-provided class objects. You can think of the Java launcher as creating 3 loaders and doing the transmission down to the VM for modules on the module path. You can see why we wanted the module system to be disinterested in class loaders. The JDK has been factored into dozens of modules, but its class loading architecture, the shape of the class loading architecture, hasn't changed. Encapsulation is provided by true VM-level accessibility, not by class loader-based visibility. So the module system doesn't need to mandate 1 loader per module. It can handle multiple modules per loader just fine. That's what the picture shows. You'll recall that I talked earlier about the unnamed module as a vehicle for compatibility. Strictly speaking, I was referring to the unnamed module of the application loader. In fact, every class loader has an unnamed module. If the VM sees a class being defined by a loader, and the VM can't associate that class with a named module that was transmitted down earlier, then the VM treats the class as being in the loader's unnamed module. As you might guess, the VM always allows access to public classes in an unnamed module. This all means that every class is a member of a module. Even classes in the jar files on the class path, junit.jar and glassfish.jar, are members of a module. It's actually it's meant to be the 7th box in the VM on the right. And if you have a class object, the getModule method will always return a sensible module object. The module system introduces the concept of a layer to associate class loaders with modules. A layer is a family of class loaders that together serve to load classes for a graph of modules. Logically, the Java launcher defines the boot layer consisting of the 3 familiar loaders. It's the boot layer that associates the Java base and Java logging modules with the bootstrap loader, the Java SQL and Java Corba modules with the platform loader, and so on. So a layer is created from 2 things, a graph of modules and a function that maps modules to loaders. On the left is the graph from resolving the JDK JLink module, which contains the JLink tool for building runtime JDK images. Just an example of a module graph. On the right is a Lambda expression mapping some of the modules in that graph to the bootstrap loader and the application loader. Creating a layer informs the module system about the packages that will exist in the program and the modules they'll come from. This is a great slide to take a picture of, hint, hint. The module system passes this information to the VM, so that when classes are eventually loaded and defined, the VM knows which module a class belongs to and what that module reads and exports. It's like the VM has a shadow copy of the module graph that it uses when checking accessibility between classes. Now, because of how class loading works, the module system must enforce certain constraints on a layer's module graph and on a layer's mapping from modules to loaders. Let's talk about the graph first. Last chance to take a picture of the slide. At the back. Very good. Oh, a bit more, one more. Okay. This is the graph of modules in JDK 9. What do you notice about it? It's a DAG. Exactly the same answer that came from over there last year. I remember. Such a precise answer. Okay. It's a directed acyclic graph, no cycles. This is the first and biggest constraint on a module graph. It's taken almost a decade to detangle the tens of thousands of classes in the JDK to the acyclic and relatively sane state that you see here. We'd like to keep it that way. In fact, one of the motivations for investing in modularization of a codebase is the knowledge that once complete, there won't be any backsliding into the ball of mud that cyclic dependencies allow. We're not the only ones who think like this. Java Application Architecture is an outstanding book about modularity. In a section titled Cyclic Dependencies, the Death Knell, it says, excessive dependencies are bad, but cyclic dependencies are especially bad. It goes on to say, generally speaking, cycles are always bad. However, some cycles are worse than others. Cycles among classes are tolerable, assuming they don't cause cycles among the packages or modules containing them. Cycles among packages may also be tolerable, assuming they don't cause cycles among the modules containing them. Module relationships must never be cyclic. This book is from years ago, nothing to do with the Java module system, but this is good advice. Let's turn to another constraint on module graphs. The second constraint on the module graph that's going to be the foundation of the layer is that a module must read only one module that exports a package of a given name. If a module could read more than one module that exports P, as X is trying to do here, in which module would P be accessed? There's no answer. The module graph is just broken. So we defend against that. Only module graphs which obey this constraint and have no cycles can be turned into a layer. That's really what we mean by reliable dependencies. Dependencies are reliable when a module can access only one version of a package at a time. There are no split packages like you get when multiple jars on the class path contain potentially different versions of the same package. Now, you might be wondering if it's possible for X to read version 1 of Y, while at the same time another module reads version 2 of Y. After all, X and the other module would each read only one module exporting P. The answer is that it's not possible because it can only work safely in certain scenarios, and outside those scenarios it's not clear that supporting it out of the box, which is to say in the Java launcher, the one that creates the class loaders, it's not clear that supporting it out the box is worthwhile. But you can all ask your questions about that in 10 minutes' time. Recall that a layer includes a module graph, for which we saw two constraints, and a mapping from modules to loaders. The main constraint on the mapping is that if different modules in the graph have a class called C, then those modules must be mapped to different loaders. This is the fundamental limit in class loading. A class loader can only create one class called C. More conservatively, we say that if different modules have the same package, not just class, then those modules must be mapped to different loaders of the layer. The mapping from modules to loaders has another constraint that's not practical to check, though, because it concerns how loaders behave at runtime. It's that the loaders must delegate to each other in accordance with the reads edges of the module graph. The reason is obvious. If module X reads module Y, then in order for X's classes in one loader to access Y's classes in another loader, X's loader must delegate to Y's loader just to find the classes, even before you can start worrying about access. As their name suggests, layers can be layered. When a graph of modules is resolved, it's actually resolved against a parent layer. Then, when the graph helps to create a new layer, the new layer picks up the parent layer. This allows a graph of modules to have dangling references, that is, requires clauses for modules that the module system will find in a parent layer during resolution. On the left, resolution has set up not only a reads edge between modules in one layer, the horizontal one, but also a reads edge between modules in different layers. Constructing a tree of layers in this fashion is the job of a framework, like an app server or a test harness. Layers give frameworks tremendous freedom to organize modules at runtime without upsetting the framework's traditional use of class loaders. It's like the invoke dynamic instruction from JDK 7, a way for framework developers to interact with the VM to reify information about the shape of a program. Let's look at one scenario where layers help out. Layers are how the module system supports multiple versions of a module. Here, an app server has created two layers on top of the boot layer. On the left, the Hadoop layer reifies a module graph with Guava version 11 and Jackson version 1. And on the right, the JavaScript layer reifies a module graph with Guava version 18 and Jackson version 2. Each module graph is well formed and mapped to loaders in a sensible way, but the modules in the Hadoop layer are not aware of the modules in the JavaScript layer and vice versa. But please note, this is all thanks to a framework creating the Hadoop and JavaScript layers. The Java launcher doesn't create layers like this. All it does is resolve the module you give on the command line, then map everything in the resulting module graph to the application loader in the boot layer. It supports only one version of each module. The reason is to avoid the nightmarish problems that occur when multiple versions of a module, or indeed any jar, casually come into contact with each other. It's really only safe to use multiple versions of a module when a framework like an app server is in control. The takeaway is this. Just as modules wrap up coherent sets of packages and interact with the VM's accessibility mechanism, layers wrap up coherent sets of modules and interact with the class loader visibility mechanism. It'll be up to frameworks to make use of layers in the next 20 years, just as they made use of class loaders in Java's first 20 years. I urge any framework developers watching to open up the JDK 9 Java doc and look at JavaLang module configuration and JavaLang reflect layer. So that was a deep dive into loaders and layers. Modules do a better job of encapsulation than class loaders, but class loaders, they're not going anywhere. Layers then control the relationship between modules, a graph of modules, and the class loaders. And assuming class loaders respect the module graph, that is, they delegate sensibly, the system is safe by construction. There are no cycles or split packages. Zooming all the way out, here are the three key points. There is strong encapsulation of modules by the compiler, VM, and core reflection. There are unnamed and automatic modules to help with migration. And the whole system is safe by construction, no cycles or split packages. In essence, the module system is a seat belt, not a jetpack. If this reminds you of the rationale for generics more than 15 years ago, you're right. Writing a module declaration makes your code more reliable and maintainable, much like writing a list of string rather than list. You always knew that your list held strings and generics let you denote that. You always knew that a package was not for general use and modules let you denote that. It's no coincidence that designing a practical module system and modularizing the JDK has taken approximately as long as designing the pragmatic generic type system and generifying the JDK. There's still a long road ahead. Although the module system is conceptually simple, there are changes in JDK 9 that probably won't break user code but might break framework code, and I'd like to go through them quickly. There are 3 areas of incompatibility in JDK 9 connected with the official definition of Java SE. First, we've removed 6 methods from the packages JavaUtil logging and JavaUtil jar. Their signatures made the Java base module depend on the Java desktop module, and no one wants that. This removal was announced in the Umbrella JSR for SE8 in 2014. In addition, we've removed 2 AWT packages that were never supported, on the right there, despite being in the Java namespace. Very sad face. Second, the Java EE types shipped with the JDK are not accessible by default. This means Corba, JAX-B, JAX-WS, the Java Activation Framework, and the JDK's subsets of the Java Transaction API and the Common Annotations API. The types are physically in the JDK image, but their modules are not read by the unnamed module of the app loader. If you're writing a module, no problem, just require Java Corba or Java XML bind or whatever. But if you're running code from the class path, you need a command line flag to activate the EE modules. Third, the version strings reported by the system properties, Java specification version, Java VM specification version, etc., have changed. Code that looks for 1 dot at the beginning of the string will fail on JDK 9 because the version strings begin with 9. There are then 3 areas of incompatibility within the JDK 9 implementation. First, we've slimmed down the sunmisc package. Sunmisc unsafe is still accessible, but sunmisc base 64 encoder and sunmisc base 64 decoder are gone. One thing you can do today is run the JDEPS tool that came with JDK 8 over all of your jars. It'll tell you if they're using unofficial classes like sunmisc base 64 encoder, and then recommend official replacements like the JavaUtil base 64 class introduced in JDK 8. Second, many JDK internal APIs are not exported. Code that tries to access even public types in the sunnet www package, or sun security x509, or comsun.org Apache Xerxes internal JAX-P, I could go on, will fail with an illegal access error. The only way to regain access is with a command line flag. Third, many internal aspects of the JDK have been overhauled, such as the layout on disk and the implementation of the 3 class loaders. Code that assumes there's a file called rt.jar or tools.jar in a particular directory will fail on JDK 9. Scripts that try to patch the JDK with -x boot class path /p for prepend will fail on JDK 9. And as I mentioned before, code that assumes the application loader is instance of URL class loader, or that assumes all JDK classes are defined by the bootstrap loader will fail on JDK 9. The module system itself tries hard to support migration, but it takes only one unmaintained library to prevent migration to JDK 9. If that library can't migrate because it's using something in comsun.org Apache Xerxes internal JAX-P, then nothing on top of it can migrate to being a module either. In this regard, modules are unusual. They suffer from a tragedy of the commons, whereas most big features like generics or lambdas let people opt in at their own pace without needing to wait for others. Last slide. As I said, the single best thing you can do to prepare for JDK 9 is fire up JDK 8 and run the JDEPS tool, which analyzes dependencies. It can tell you if your code or code that you rely on will be affected by the changes in 9. Please try the JDK 9 early access binaries on java.net. The module system has been present and active doing the encapsulation for the JDK modules since March 2016. Plus, the JDEPS tool in JDK 9 is more accurate than the one in JDK 8. Everything you ever wanted to know about the module system, including much of what I've said here, is discussed in JEP 261. I cannot emphasize enough how much valuable information is in JEP 261. There's also JEP 260, which defines those JDK internal classes to be exposed in JDK 9, and JEP 223, which defines the new version strings beginning 9 dot, and JEP 220, which describes how rt.jar has gone away. And finally, JEP 200 gives an overview of the JDK modules, but if you've already read JEP 261, there won't be any surprises in 200. And with that, at 56 minutes, thank you very much. And we will take questions. I think we can do 50 minutes. Someone has been charging their iPhone. No wonder it went so slowly. Everything was, yeah. So if you have a question, please come up to the front. We cannot hear you if you stand where you are. I promise, we're not making it up. We can't hear you. So if you have a question, please come and use this mic here. Is it a different question, Ian, than the ones you've asked before?
Yeah, it's a different question. So one thing that I've always found odd, in Tomcat, they try to prevent class loader leaks by nulling out all static fields when you unload a web app. I'm assuming that won't work anymore?
It will work if they do the right thing.
How do they make that happen?
Because they're loading the classes. The Tomcat, if the web app is itself a module, but all of its classes are loaded by Tomcat, Tomcat is a deity. It can rewrite module declarations on the way in. It can choose to export just to itself, by the way, or to one of its modules, any packages it needs to reflect over, although whether it actually needs to do what you've just said sounds like an optimization that you may not need on.
Is this mic on?
Yeah.
Okay. There's also a specific list of issues, in quotes, that Tomcat has with the JDK and where it's gone into the JDK and nulled out fields and things like that. Many of those issues have actually already been addressed. In fact, over the last couple of builds, there's some specific fixes in the JDK specifically for these type of issues that Tomcat ran into.
Thank you.
Actually, the maintainers of Tomcat, I think Mark Thomas in particular, has been proactive in actually finding these issues and sending bug reports.
Well, the person who had a question there has left, so that was a successful strategy. Yes, please.
What is going to be the fate of shaded jars and Uber jars?
Where's Robert? Oh, he's right behind you. A question for Maven. I don't know. Ask the Maven committer. So someone.
Sorry, they can't hear you.
It's not only a Maven problem. It's about shading is about creating an Uber jar, and there you have all the classes just inside one jar. So you have lost your encapsulation. So I know that Mark has one thing about that on his issue list. So we're just waiting for an answer or a proposal for it.
No more questions? Okay, please. Wow, we've really raised the barrier to entry is very high, so no one has questions anymore.
Can you give an example, like on this slide you have here, what would manage like this Hadoop layer, this JavaScript layer?
Tomcat. I mean, it's hard to get across how disinterested we are in class loaders. If you're a framework that's spinning loaders today, it all still works. You can even load classes from modular jar files. If you're the framework and you're ignoring the module info.class file, okay, that's your lookout. But if you want to respect the modular dependencies and encapsulation, the web app code itself,
That's back on you then.
right, it's up to the container to not ignore module info.class files, to load them, and when you load them, the whole point is that a module says not only what it exports, but what it depends on, and hopefully Tomcat will be able to call the module system API to resolve those dependencies and spin up a small layer with exactly the same class load as it had before, but with the classes of that loader now known to be members of a module, the module to loader mapping told to this new layer. So the graph of class loaders will look the same at runtime, if you could visualize it.
Yeah. So something else I thought of is do you export resources then too, or do they follow the same rules?
Yes, there are some rules about which resources the exports keyword is it takes package names. This is a good question. You don't specify resources like that, but they are mostly, the useful resources are exported for reflective access, which is how you get to them, right? Yes.
So do
So
they
for
need to
free.
be in like a, sometimes you put resources in they're like the same namespace as your package, other stuff you don't. Just kind of like convention. So does everything now need to be in a Java package by convention?
Oh no. You can still have your resources in metainf. And what's the rule for whether they're exported or not?
If they're in a namespace that maps to the package, then it has to be exported. If you've been in top-level packages that aren't in top-level directories that aren't really packages, like meta-inf is not a valid package name, then they'll just continue to be able to locate and access them as you always did.
Okay.
Just
And there's the exception for class.
yes, there's in the updated proposal there is a specific exception for .class files because there's many tools need to access class files, so they just worked. Can I just say one thing just about the layers on your first part of your question is it doesn't actually require a sophisticated app server to use layers. There's actually many tools may actually use layers as well. So for example, the Java C compiler loads annotation processors that are deployed as modules in their own layer. The JLink tool has a plugin interface. You can actually deploy plugins as modules, and they will actually be loaded into their own layer. It's parented to the boot layer. So there's many tools. Okay, we're all done.